Okay, folks on Zoom, can you hear me?
Yes, we can. I can hear you.
Great. Okay.
I can hear you.
I can hear you.
Good, thank you. Okay, can everybody say that?
Yes.
All right, and okay, do the slides move?
Yep.
Okay, good.
That was halfway through my quarantine, so I was like, I wanted to be. Yeah, no, I know. It was one time I went in and asked him for help and he couldn't do any of the problem. Yeah. Yeah, that sounds nice.
Where's Jenna?
This was the answer random my life.
Yeah.
Now that also releases my implement.
Yeah.
Okay. I was just wondering.
Yeah, it's going to release a bunch of things. That's why it's so dangerous for your kidneys. Oh, okay. Okay. So, okay, yeah. So you'll see, Jenna, no, you already had that class. Never mind. Never mind. Okie dokie. Artichoke. There we are. All right, time to start. We were talking last time about the use of coupling reactions that you take high energy molecules, usually phosphorylated, most of the time at least. You couple the hydrolysis of the high energy phosphate bond. That reaction is combined or coupled with another reaction that is less likely to go, that's less favorable thermodynamically speaking. By putting the favorable reaction together with the unfavorable reaction, the favorable reaction pulls along the unfavorable reaction. That's called reaction coupling. That is used very, very commonly in cells to get unfavorable reactions to go. Now, you also have several different enzymes that are going to help manage ATP and ADP concentrations inside cells. So the ADP molecules will get phosphorylated. When they get phosphorylated, they give you ATP. And you can therefore mediate the concentration of ADP in order to make sure that you're just one step away from making an ATP. So there is an enzyme called adenylate kinase. Adenylate kinase, very widely distributed enzyme, found in lots of different organisms. It will take two ADPs, convert one into ATP, the other into AMP. This reaction is reversible. So this can help replenish your ATP concentration or if you're short on ADP, the reaction can actually go the other way. So that's adenylate kinase. Adenylate kinase. This will help you increase levels of ADP inside cells if the concentration of ADP falls too low. You can also use it to help replenish ATP stores. If they fall too low and you have plenty of ADP around, you can use that to get ATP as well. So this enzyme can kind of do double duty inside the cells. It's a very useful enzyme. Creatine kinase can take the high energy phosphate from phosphocreatine and transfer it to ADP. And this will give you ATP plus creatine. This reaction, of course, can go the other way. If you're trying to make phosphocreatine in order to store energy to replenish ATP, this is used again mainly in muscle. But this reaction can go either way as well. And remember, phosphocreatine is a storage enzyme for energy. It's used to recover after the muscle has been working very hard. So phosphocreatine is made by creatine, ATP, and creatine kinase. But you can also go the other way if you want to replenish ATP stores in very heavily worked muscle as well. And if that wasn't strange enough, some bacteria store little bodies called volutin bodies. Volutin bodies. Oh, what's a volutin body? A volutin body is polyphosphate. So it's a bunch of phosphate that's linked together with phosphoanhydride bonds. So essentially it's blah, 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 so on and so forth. So it's a polyphosphate body. Bacteria tend to use this. And you see them in bacterial cells if they're very well fed. And you can see these little dense bodies kind of floating around in them. So they have an enzyme that's called polyphosphate kinase. And they use all this extra ATP essentially to link a bunch of phosphate together, and it forms this little body inside the cell. It's really kind of cool. Called a volutin body. You can stain cells for volutin bodies. Volutin. Volutin bodies. And if things start to get a little rougher, energetically speaking, they can take phosphate from the polyphosphate body and clip a phosphate off and put it onto ADP to make ATP. So this enzyme, polyphosphate kinase, can actually work both ways too. So it can be used to store a big, massive polymer of phosphate, and it can also be used to stick that phosphate onto ADP to make ATP. Pretty ingenious.
So I'm curious because you can use this polyphosphate to make ATP when you need it, but then to make polyphosphate, you do use ATP.
Yeah, if you have more
Where do you get
ATP,
the ATP to make it then?
well, if you have more energy than you need, you start storing rainy day stores. Bacteria don't store fat. Some will store glycogen. The photosynthetic bacteria store starch. The other thing they store is polyphosphate. So that's their rainy day stores as energy goes. Because they don't tend to make a lot of extra protein that they can cannibalize. So bacteria get creative when it comes to storing energy. That's one of the ways they do it. The other way they do it is something called a PHB body, polyhydroxybutyrate. They store polymers of polyhydroxybutyrate. And in electron microscope, those look like big whitish bodies inside the cell. And PHB is another way they store energy. So in times of need, if you want to charge up that ATP, you just take phosphate from the polyphosphate body and stick it onto ADP to make ATP. And that enzyme will do it. It just works the other way. Now we come to oxidation reduction reactions. Oxidation reduction reactions. The movement of electrons from one molecule to another are used a great deal in biological systems. So the transfer of electrons can do biological work. And when you think of Gibbs free energy, if you guys have had this hammered into your head by Dr. Neidegger, the other Dr. Neidegger, he's probably told you that Gibbs free energy, it's a potential energy. It's a thermodynamic potential energy. Okay, Andrew's sitting there nodding his head. You've heard that before. So when we think of energy from so-called standard redox potentials, that is very much a potential energy, but it's a potential energy that is an electrical potential energy. By that I mean it's a tendency for electrons to get passed between redox pairs. That's what that is. So if you think of both of them as potential energies, I think it will make that a little easier to get your head around. Okay, Greg's nodding his head like, you feeling me? Yeah, cool. All right. So electrons are going to flow from molecules with, relatively speaking, low affinity for electrons to those that have, relatively speaking, a higher affinity for electrons. And we're going to use a kind of arbitrary standard, and we're going to set it to 0. And then we're going to grade reactions according to that standard. That standard is a hydrogen cell. That's a hydrogen cell. So the redox potential is measured as an electromotive force. An electromotive force. You can think of this as the force, or if force doesn't work for you, maybe the pull, the tendency for electrons to flow from one to another. And it's going to be proportional to these differences in electron affinity between these two moieties. Now we're going to be able to measure those electron affinities relative to the hydrogen cell. That's how we're going to get these numbers. And that force, that's driving the electrons, pushing the electrons, pulling the electrons, whatever. That's called electron motive force, or EMF. I realize EMF sounds very military, probably, but that's what it's called. Cells will couple EMF to motors. These motors are going to be electron energy transducers, and that's how the work is going to be done in the cell. In our cells, our end of the road electron acceptor will be molecular oxygen. Now, many cells use molecular oxygen as their terminal electron acceptor. Not all cells do. Yes, our cells do. Yes, terrestrial life on this green Earth use molecular oxygen as their terminal electron acceptor, but there are a whole lot of organisms out there that don't. So don't fall into this trap that students often fall into. Oh, they transfer electrons, so they must transfer it to molecular oxygen. No, maybe they don't. If they're air breathing, yeah, they probably do. But there's many ways to skin the metabolic cat, so to speak. So please don't fall into this trap that all organisms use oxygen as their terminal electron acceptor. Now, oxygen is a good molecule to use as a terminal electron acceptor. Why? It's as greedy as a day is long for electrons. I mean, this is the Gordon gecko of electrons. You guys have no idea what I'm talking about. The movie Wall Street with Michael Douglas, he plays Gordon Gecko. He gives that speech, greed is good. No, Aaron hasn't even seen it either. Okay. Gordon Gecko is supposed to be he's supposed to be the personification of greed. And so molecular oxygen is the Gordon Gecko of electron transports, because it's a Gordon Gecko of electron affinities. It really wants electrons. So electrons will be passed around cells, typically through carriers. Some of those carriers will be soluble. Some of them will be membrane bound. And ultimately, this passage of electrons through an electron transport chain will be used to make a proton gradient. That's then used to drive the F-type ATPase. That'll be used to make ATP. Yet another example of an energy transducer. So electron transport type reactions, redox reactions, must occur in pairs. Think about it, gang. Can you take electrons and throw them off into the wild blue yonder? No, not very stable. So you must have a paired reaction. Somebody's going to be the loser of electrons. Somebody's going to be the gainer of an electron, or pair of electrons for that matter. You got to have a loss and you got to have a gain. Identifying who's losing, who's gaining is a very key part of working out these reactions. Let's consider a really, really simple example, one I'm sure you've seen before, but let's give it a try. So we have iron 2 and copper 2, and iron will lose an electron to copper. And if you have been in an old house, you might have seen people who've put iron pipes and hooked them to copper pipes without a dielectric, and you've probably seen what happens. Our old house, yeah, somebody didn't have very much of a chemical education, and there was this big pile of oxidized material where the two pipes went together. So now this will have two half reactions, will it not? Who's the loser of an electron? Iron. Who's the gainer of the electrons? Copper. All right? Then let's express this in a couple of half reactions. So let's talk about first the oxidation reaction. When something is oxidized, what happens to its electrons? Loses. So remember, oxidation involves loss of electrons. Reduction involves gain. Oil rig. Okay, Salma's looking at me as if to say, okay, you're just too impressed with yourself. Just get on with it. Mm-hmm. All right, I'll get on with it. Mm-hmm. Oh, okay. Oil rig, okay, so, all right, or Tom is Leo, the lion goes grr, or something like that. Okay. All right, so let's do a little mental exercise then. Seeing that you guys are all quite chemically well versed, go ahead and draw the half reaction for the oxidation part of it. Go ahead. So who's oxidized? The loser. The loser is iron. So go ahead and draw the iron half reaction. Okay, did you get it? Should look something like that. Iron 2 goes to iron 3. Well, if it's iron 3, then there's an electron that is missing, so you have to put it over here. With oxidation, your electron will be on the other side. Now, let's do the reduction half reaction. Go ahead and write that out. Now the electron is going to be over here. Get it? Look like that? Now, if you add these two reactions, what happens to the electrons? They cancel. If you add these two together, do you get this reaction? If they, yeah, I hope so. If they do, you probably did it right. So you have an electron donating agent. The electron donating agent is oxidized. That electron donating agent, even though it's getting oxidized, is called the reducing agent. In biology, we're going to tend to call it the reductant. The reductant. Then an electron accepting agent. It will be reduced. It will be reduced, but because it's contributing to the oxidization of something else, it's called the oxidizing agent or oxidant. Oxidant. So, in a redox reaction, you have a reducing agent and an oxidizing agent. So if we take a look at this reaction, this is the electron donor, right? So it's the reducing agent or reductant. This is gaining the electron. It is being therefore reduced. Therefore, that's the oxidizing agent because it's contributing to the oxidization of the iron. So that would be the oxidizing agent or the reductant or the oxidant, excuse me. Very good. So these half reactions essentially show you who is the donor, who's the acceptor, who is the oxidizing agent, who's the reducing agent, so on and so forth. Now, we call this sort of half reaction, it's going to act as a so-called conjugate redox pair. Conjugate redox pair. Iron 2 and iron 3, they act as a conjugate redox pair. Now, can organic compounds undergo oxidation reduction reactions? You bet your femur they can. So, and it's the same sort of principle as previously described. So we have this aldehyde. This aldehyde is going to be oxidized, and it will be oxidized to a carboxylic acid. So can you write the half reactions for this? Go ahead. Okay, see some of you are done. Okay, a few of you shook your heads. Okay, hey, you guys on Zoom, don't be sloughing on this. You guys write this out too. Okay, see a few of you look like you're done. I'll break the suspense for you. Did you come up with something like this? Or close to it? Okay, a couple of you are nodding your head. Some of you are going, yeah, sort of close, okay. And if you add those together, you should be able to get this reaction here. The hard part about that is you probably didn't want to split the hydroxyls. That's not obvious when you play with it. It works quite well if you split the hydroxyls. So in biological reactions, very typically, your electrons will be paired with hydrogen ions. And the reaction that is an oxidation that involves electrons paired with hydrogen ions, those are typically called dehydrogenations. And enzymes that participate in such redox reactions are usually referred to as dehydrogenases. Now, here's the interesting part, because in chemistry, these particular ions are not that common, and they are hydride ions. So hydride ions are hydrogen ions with a -1 charge. -1 charge. So it's a hydrogen ion with a pair of electrons. Not terribly common in chemistry, but pretty common in biology. In fact, one of your carriers, NAD and NADP, will carry electrons in the form as a hydride ion. And these oxidation reactions also can occur through combination with oxygen in cases like that, in the case of things like mixed function oxidases and things like that. So there is a term in biology, in biochemistry, if you are removing 2 electrons and 2 protons, say, for example, and they're paired, you're removing what's called a reducing equivalent. A reducing equivalent. So, thinking back to physics, or maybe you're in physics right now, remember that when you calculated work, work tends to be the product of a so-called intensity factor and a capacity factor when you're calculating work. That tends to be the things you multiply together to calculate work. If you're going to have an electrical charge moving through a difference in electrical potential, can that be used to do work? Sure it can. Sure it can, absolutely. So in a case like that, your work will be equal to the charge times the difference in electrical potential. Now, if work is negative in this case, that means that your work is being done. It's negative because energy is leaving the system. It's leaving the system. I see a lot of heads nodding. This is starting to make sense, I think. Okay. This equation, how useful is it for our purposes? Not too. Why? Because in biochemistry, we deal with moles and things like that. So can we gussy this up a little so that it's more useful for our purposes? Well, that right-hand side of the equation over here, what if we were to multiply this by the number of electrons transferred and then multiply it by Faraday's constant? What is Faraday's constant? Faraday's constant is the number of its electrical charge on a mole of electrons. So if we were to convert this into something a right bit more useful for our purposes, we'd simply take charge and we'd convert it to this. It'd be number of electrons times Faraday's constant times delta V. And that would be essentially the energy difference that we're looking for here. Work rate, this could be delta mu or, or whatever. Okay. Now, in a case like this, the greater, can you see that the bigger this is, the bigger that's going to be? So the reaction you would expect would be spontaneous if this number is greater than 0, right? Yes? Okay, well then you can actually take this puppy here and you could, oh, sorry, this would be, there. Sorry, minus sign there. My bad. In fact, this, sorry. My physics is rusty, sorry. So if you're going to then rearrange this so that you could potentially use this, you could say that your delta V is now going to be over your divided by now this. That number there, can that be a number that is dependent upon the proportion of reactants and products? Yeah, it can. So this then becomes right? And from this, we get this very useful equation that was the product of the German physicist and chemist, Walter Nernst, and that's the Nernst equation. We'll get to the Nernst equation in a couple of slides. I just wanted to show you this equation doesn't come from outer space. It does come from something useful. Okay, so the tendency of a molecule to get rid of its electron, grab an electron from somebody else, that's referred to very simply as its reduction potential. You express this in volts, and you measure it as the standard reduction potential, delta E, with a little degree sign. You calculate that experimentally. Again, you're going to calculate it versus the hydrogen cell. So this half reaction, you're going to put that essentially at 0 and then measure everything else relative to that. Will it take electrons from this? If it does, it's positive. If it gives electrons, it's negative. And from chemistry, remember you do this at 101.3 kilopascals worth of hydrogen is bubbled into a 1 molar solution. So its pH is very low. And you have a salt bridge in between, and then you measure the EMF using a gauge, essentially. And that's how you do that. Now, how useful is this for biologists? That might work for our stomach. It's not going to work for the rest of our body, is it? So then for biochemistry, we have a biochemical standard reduction potential, and that has a E with a degree and then a little prime. And those are also experimentally derived, except instead of at pH 1 molar, it's going to be at pH 7. And same thing, electrons flow either through the salt bridge to the reference solution or to the hydrogen electrode, depending upon the tendency of the solution to grab the electrons or not, and what have you. And those flow of electrons you measure as electric current. That's why it's measured as volts or millivolts or whatever. Okay. So the Nernst equation, oh dear, there should be a N right there, sorry. N-E-R-N-S-T, Nernst. Yeah, all apologies to good old Walther. So the Nernst equation essentially, which essentially flows from this up here, you have the reduction potential equals the standard reduction potential plus or minus, plus, well, not plus or minus, plus universal gas constant, temperature in Kelvin, divided by number of electrons, times Faraday constant, times the natural log of the acceptor, divided by concentration of the electron donor. Again, R is the gas constant, T. You do these at constant temperature, so you do them at 298 Kelvin, and then F is Faraday's constant. 96,494. 480, 94, something like that. Kilojoules per volt per mole. Just get your chemistry textbook. It's in the back of your chemistry textbook. It's those constant that you have at the other, or maybe it's on the other side of your chem book. It's there. Trust me, it's there. Some of your TAing, the chem textbook has a bunch of constants. Yeah. Okay, yeah, it's there. Just look it up. It's there. On the board, you have a negative. Right, and then on here we don't have. Oh, okay. Right, acceptor, donor. Yeah, that too, yeah. All right, so this business here, you can just calculate as 0.026 volts divided by number of electrons, so on and so forth. And then your E ends up being the electron motive force And then this equation will be used to derive this number for your test compound. And then for biochemistry, you do this at pH 7. So you still bubble hydrogen gas through, it's just you're not doing it in a pH 1 or pH 0 solution, it's pH 7. And so now the standard biochemical reduction potential for your hydrogen half cell is minus 0.414 volts. And Albert A. and his crew, and then a bunch of his postdocs went out and they calculated a bunch of these. And in your book, there's a big table that has the standard biochemical reduction potentials for a bunch of biologically significant molecules. Now, let's interpret these particular numbers that you get. If those numbers are really highly negative, means they're good donors and lousy acceptors. Good donors, lousy acceptors. If those numbers are highly positive, then they're great acceptors and lousy donors. You can guess what oxygen is. Oxygen's on the positive side of the street. It's the Gordon Gekko of electrons. So here's this nifty table I was talking about from your book. And you can see essentially, here's molecular oxygen. Oh, doggy, that is pretty positive. Then we get set at 0 hydrogen. Then we get all these other things essentially involved in biology, so on and so forth. And here's conversion of oxygen to hydrogen peroxide, and then various types of iron, nitrate, and so on and so forth, and blah, 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 what have you. And this comes from the Loesch book, Handbook of Biochemistry and Molecular Biology. That book essentially from CRC Press was kind of the Bible. It's got, I think this goes on for close to 20 pages in that book of redox potentials. My brother found a hand-me-down version of this book, and as a joke, he got it for me for Christmas. And I mean, the thing, you can choke a mule with that thing. It's big. Thing is, I took it with me to UC Davis and I used it almost every day. And I didn't have to look stuff up. I just had it right there. And students were coming down to my dorm room to borrow it. And I was famous. I was ready to charge for it and make money, but no, I didn't do that. Anyway, yeah, that thing was a backbreaker. Now, can we relate our electrical potential to our thermodynamic potential? We should be able to. If Maxwell's laws mean anything, then this should be something that's doable, and it is. And here's the equation. And once again, we have old Faraday's constant, which you can get from the back of your chem book. Or, okay, you sold your chem book back, fine. Just look it up online. Siri, what is Faraday's constant? That easy. So that gives you delta G, and notice that this works for the standard biochemical free energy change and the standard biochemical reduction potential. Okay, cool. Let's apply this. So here is a redox reaction. This occurs in your muscles when your muscles get to the lactate threshold. So let's say our dear Olivia's on the field, running up and down the soccer field like good midfielders do. And, oh, Liv, don't give me that look. And running, she's running a lot. She's getting really tired. Pretty soon, her fast twitch muscles are going to not work anymore because they filled up with this stuff, lactate. So the pyruvate that gets generated by the oxidation of muscle glycogen and then glucose, now pyruvate will be used as a dumping ground for electrons, and you make lactate. So you're essentially going from this that's pyruvate to this. And you're using so this is an oxidation reduction reaction, right? Let's analyze it. Let's calculate some numbers from it. So to get started, half reactions, right? So we have one half reaction, pyruvate to lactate. We have the other, NAD plus 2 NADH. And we have these are very well established. We have the delta E's for these. Those, in fact, come straight from the tables in your book. So looking at these values, we would suspect the reaction, if it's going to proceed in the forward direction, you're going to have NADH giving its electrons to pyruvate because that's more negative. Therefore, that's going to be the giver. This will be the taker. Right? More negative, it's a better giver. More positive, it's a better taker. Who's the better giver here? Who's the better taker? Better giver, better taker. Yes? Let's use chemical terminology. More likely to be oxidized, more likely to be reduced. Okay, these numbers are additive. So our biochemical free energy change, biochemical reduction potential for this will be 0.19 volts minus, remember, you go to the barn and you get the red ox. The red ox, you do what's reduced first minus what's oxidized. The red ox. Selma, I don't know how you teach that, but that's how I remember it. The red ox. Yeah, throw the puns out there and yep, there you go. And if you do this, you get a positive 0.13 volts. If it's positive, it will tend to go in the forward direction. Okay, that's our standard biochemical reduction potential. Now let's calculate standard biochemical free energy. Using this equation, put it in, zaba boom, there we are. And it's negative, so that should occur spontaneously from a thermodynamic perspective. Then, if we really want to get fancy, we want to calculate the KEQ. We use this equation here. We stick this number over here. These we know. Divide that by that. Take the antilog and Bob's your uncle, and there you are. Boom. 10.13. If I stick this on a test, so you think you could do it? N? Electrons, yeah. Where? Here?
My delta T equals minus 2.
Oh, here. Yeah, I just put it there so you can see they cancel. And yeah. And then natural log, do the anti-log, and there's your KEQ. All right. Oh, and you don't need to memorize equations. I will give you equations. I will give you equations. Yeah, these ones. I should be able to give you tables, though, and you should be able to use them. If I give you the equations, then you should be able to calculate these numbers here. So your big, huh?
The way it is written on the fire rate, 2 NAD plus 8. I suppose because there's 2 hydrogens. I was just looking to see.
Well, yeah, one of those goes into yeah, NAD just carries 1 hydrogen. It carries 2 electrons. The other one goes in solution. That's why there's 2. 1, 2.
Right, so I was just looking to see where the 2 electron transfers from.
Yeah, there's 2 because this carries that as a hydride.
Okay.
So there's 2 electrons there, but there's just 1 hydrogen.
And then
The other one's in solution. Yeah. NAD is weird that way. Flavines will carry 2 electrons, 2 hydrogens. NAD and NADP don't. Okay. So the two big players, not the only ones, but definitely the ones most used for redox reactions in cells are NADH and NADPH. NADPH tends to be used more for anabolic reactions. NADH is used more for catabolic reactions and energy yielding processes. So the basic structure of these molecules is you have an adenine and a ribose, and then 2 phosphates. So this is ADP. And then you have another ribose and then a nicotinamide. That's NAD. For NADPH, you just stick a phosphate right here. That's the only difference. That's the big difference. Now, this molecule, this nicotinamide molecule, is planar. So when the hydrogen becomes a part of this, it will have a tendency either to be above or below the plane of the nicotinamide ring. So as you can see, if it is above the plane, it's called the A side. If it's below the plane, below B, is the B side. A above, B below. Now, why is this significant? Well, 3 things. 1, NAD and NADP, for this matter, when they are reduced, they have a distinct change in their absorption at 340 and 320 and so on and so forth. This means that enzymatically, if you want to do some sort of enzymatic assay, the production of NADH can be very, very easily measured by taking a look at its absorption at 340. Because NAD, as you can see, doesn't absorb worth a whit at 340. However, when it's reduced, it now absorbs pretty robustly at 340. So this is extremely useful for assays. And there are many NAD using enzymes that are very good assays to determine the presence of mitochondria, the presence of chloroplasts, the presence of peroxisomes, a certain, presence of, well, peroxisomes is usually catalase, that's done, but there are other NAD using enzymes that are used and what have you, and this is quite useful. Now, why make a big deal about A and B? Reason for this is that dehydrogenases that use NAD, they specifically put the donated proton hydride on the A side or B side. So there are A side specific dehydrogenase and B side specific hydrogenases. In fact, there's over 200 enzymes that use these as cofactors. And they're called oxidoreductases, or more commonly, dehydrogenases. And the nicotinamide ring, again, will carry that as a hydride. So the nicotinamide goes to the reduced form here. And again, that's planar. That's planar. The other proton just goes into solution. And here are some of these, and you can see they have stereo specificity for where they put that reducing hydride. Do they put it on the A side or the B side? These enzymes are specific for it. So there's an absolute stereo specificity when it comes to the reduction of NAD and NADP for where the donating hydride goes. It's really quite remarkable. And we're out of time. We'll finish flavines, and then we will start on glycolysis. Every step, every enzyme, every intermediate, it'll be glorious. You just wait. Okay, gang, I'll see you guys maybe, well, some of you. Wednesday, some of you, tomorrow for lab. Take care, stay well.
Question for you, Dr. Bradovich.
Yeah, Jenna.
So I don't have COVID or anything. I just have a regular cold. Are you comfortable if I come to lab tomorrow?
Depends how you feel.
Okay. I'm trying to just take as much like decongestant as possible, so hopefully tomorrow I'll be good.
Okay.
Is it okay if I turn the homework in then too?
Yeah.
Okay. All right. Thank you.
All right. Ciao.
I had a question too, Dr. B.
Yeah, Crystal.
Do you want me to try to give somebody my homework and then they can turn it in like the hard copy, or would you just rather
That'll
have me
work.
take pictures and then
That'll work.
have somebody else give it to you?
Yeah.
Hey, Crystal, I live
Okay.
next to you. Give it to me.
Okay, sweet. Thank you.
That was Amanda, as you well know.
Yeah. Awesome. Thank you.
Okay.
Bye.
Bye.